On Wednesday, April 10th, the world was treated to something unprecedented, the first ever image of a black hole. Specifically, the image captured the supermassive black hole, or SMBH for short, at the center of M87, or Virgo A, a supergiant elliptical galaxy in the Virgo constellation. This accomplishment drew on more than 10 years of hard work involving astronomers, observatories, and scientific institutions from all around the world. But how exactly did they achieve this impressive feat? They did so using something called the Event Horizon Telescope, or EHT for short. The EHT is essentially a planet-sized radio telescope made by linking up observatories from around the world. At present, the EHT consists of 8 sites, which include the James Clerk Maxwell Telescope at the Mauna Kea Observatory in Hawaii, Large Millimeter Telescope Alfonso Serrano on Volcan Sierra Negra near Veracruz, Mexico, Combined Array for Research in Millimeter Wave Astronomy in Eastern California, Kitt Peak National Observatory's 2 radio telescopes located just south of Tucson, Arizona, Arizona Radio Observatory's Submillimeter Telescope in southern Arizona, European Southern Observatory's Atacama Large Millimeter Submillimeter Array in northern Chile, 30-meter telescope in southern Spain, which are operated by the Institute of Millimeter Radio Astronomy South Pole Telescope at the Amundsen Scott South Pole Station. By combining radio antennas and data from several very long baseline interferometry stations, the EHT is able to achieve a level of resolution that allows scientists to view the intermediate environment around black holes, called the event horizon. This was no easy task, given the extreme nature of black holes. Originally predicted by Einstein's theory of general relativity, black holes are essentially what becomes of particularly massive stars once they reach the end of their lifespan. At this juncture, when a star has exhausted the last of its hydrogen and helium fuel, it undergoes gravitational collapse. This leads to a massive explosion known as a supernova, where the star blows off its outer layers. Depending on the mass of the star, the result will either be a stellar remnant or a black hole. In fact, the term black hole is a bit of a misnomer, since they are actually extremely compressed material that contain an extraordinary amount of matter within a tiny area. Because of their compact nature and very high density, they exert an extremely powerful gravitational force from which nothing, not even light, can escape. Because of this, scientists were only able to infer the existence of black holes based on the effects they have on their surroundings. This includes the way they distort space-time, causing objects around them to fall into eccentric orbits, and the way that gravity pulls this into a disk around the black hole, which is heated to hundreds of millions of degrees. The project's targets were 2 black holes with the largest apparent angular size when viewed from Earth. These are the SMBH, located at the center of the Milky Way, or Sagittarius A, and the SMBH at the center of the galaxy known as M87. In order to capture an image of these SMBHs, astronomers needed a telescope of unprecedented resolution. This is where the EHT came in. Through its 8 observatories, the EHT recorded millions of gigabytes of data of these 2 black holes. In total, each telescope took about 1 petabyte, 1 million gigabytes of data, and recorded it onto several Mark 6 units, data recorders that were originally developed at Haystack Observatory. It should be noted that since 2017, the EHT has added 3 more observatories that also participated in this large task. After the observing run ended, researchers at each station packed up the stack of hard drives, which were then flown to the MIT Haystack Observatory in Massachusetts, USA, and the Max Planck Institute for Radio Astronomy, Bonn, Germany. Once there, the data was cross-correlated and analyzed by 800 computers that are connected through a 40 Gbit S network. Converting this data into an image, though, required developing new methods and procedures. This involved comparing images among 4 independent groups of scientists using 3 different imaging methods, whose algorithms were designed and led by Catherine Bauman. Bauman worked as a postdoctoral researcher with the Event Horizon Telescope project, where she applied emerging computational methods to push the boundaries of imaging technology. In addition to verifying and selecting parameters for filtering images taken by the EHT, she helped the imaging framework that compared the results of different image reconstruction techniques. After the publication of the black hole image, a photo of Bauman smiling in front of a computer screen began to go viral on the internet. After the black hole picture was revealed, Bauman posted a photo of her and her research team with the caption, "I'm so excited that we finally get to share what we have been working on for the past year." The image shown today is the combination of images produced by multiple methods. No one algorithm or person made this image. It required the amazing talent of a team of scientists from around the globe and years of hard work to develop the instrument, data processing, imaging methods, and analysis techniques that were necessary to pull off this seemingly impossible feat. Seemingly impossible, indeed.